In this video, we're going to talk about how oxygen is transported in the blood. Bienvenidos a mi canal otra vez. Hey guys, what's up and welcome back to my channel. Today we're going to focus on the two mechanisms of oxygen transport in the blood, with a specific focus on everyone's favorite globular friend, hemoglobin. And we'll even get to take a look at some fun graphs. Okay, I know. Everybody try to contain your excitement. I'll give you some fun clinical facts along the way. And once again, I'll put some physiology resources in the description below. So without further ado, grab your chai latte and a notebook and let's get started. All right, let's start talking about gas transport in the blood. So oxygen can be transported in two ways. It can either be dissolved in plasma or it can be transported bound to hemoglobin. Only about 2% of oxygen is actually dissolved in the plasma, but the other 98% is transported bound to hemoglobin. The number of oxygen binding sites that we have depends upon the amount of hemoglobin we have in each red blood cell. So clinically, we can estimate the number of red blood cells we have and the amount of hemoglobin in each red blood cell, and we call this value our mean corpuscular hemoglobin. Or we can determine the amount of hemoglobin in the blood, which we measure in grams per deciliter of blood. So from this information, we can deduce that anything that decreases the number of red blood cells or decreases the amount of hemoglobin in a red blood cell can therefore affect our blood oxygenation. And this is a problem with anemia. Each hemoglobin has 4 iron heme groups that are surrounded by a protein chain. There are alpha chains and there are beta chains in most adult hemoglobin. The center heme group binds reversibly with 1 oxygen molecule, and 4 heme groups means that 4 oxygen molecules can be transported per hemoglobin molecule. So the iron in heme groups is why people with iron deficiency can be anemic. Anemia literally means a lack of blood. In iron deficiency anemia, people lack iron, and if they lack iron, then they cannot make enough hemoglobin, which means that they cannot carry as much oxygen. And we will talk about the signs and symptoms of iron deficiency anemia in later lectures. Hemoglobin bound to oxygen is called Oxy-Hemoglobin, and it is abbreviated HbO2. So oxygen-hemoglobin binding obeys the law of mass action. And the formula for oxygen-hemoglobin binding can be found here. So if the oxygen concentration in the blood increases, then this reaction moves to the right, and more oxygen gets bound to hemoglobin. And the way that I think of this is because if oxygen increases in our bloodstream, then there is an excess amount of oxygen, and hemoglobin needs to fill up all the empty spaces that it can with oxygen. But if we don't have as much oxygen in our blood, then the hemoglobin will release some of the oxygen that it's carrying, that way the plasma can have more, and the equation shifts to the left. From this equation, we can see that the amount of oxygen that's bound to hemoglobin depends upon the amount of oxygen that's dissolved in the plasma and surrounding the red blood cells. Okay, so let's look at this diagram. At the lung, oxygen diffuses across the alveolar membrane and into the plasma. Then the plasma oxygen actually diffuses into the red blood cells where it can be bound to hemoglobin. And the hemoglobin fill up with as much oxygen molecules as they can, and once they are filled, then the oxygen just diffuses into the plasma and it stays in the plasma to be transported there. But remember, only about 2% of the oxygen is actually dissolved in the plasma. So the blood picks up as much oxygen as the number of red blood cells that it has, and as the PO2 of the plasma will allow. Okay, so now blood is transported to the tissues, and the process that we saw earlier will reverse. The oxygen that's dissolved in the plasma will go into the cells. This creates a vacancy for the oxygen in the plasma, which means that now hemoglobin will release its oxygen molecules, and those oxygen molecules that hemoglobin releases will go into the plasma. And from the plasma, those oxygen molecules will then diffuse into the cells. And the oxygen that diffuses into the cells is used for cellular respiration. so now let's talk about the percent saturation of hemoglobin and factors that can affect this. So the percent saturation of hemoglobin equals the amount of oxygen that is bound to our hemoglobin divided by the available amount of oxygen. And in order to get a percentage, we multiply this by 100. Okay, so when we say percent saturation of hemoglobin, we are asking how many binding sites on hemoglobin are actually being used up by oxygen. How saturated is hemoglobin with oxygen? If all the binding sites have oxygen on them, then hemoglobin is 100% saturated with oxygen. But if only half the binding sites have oxygen on them, then hemoglobin is only 50% saturated with oxygen. So we can actually utilize a graph to illustrate the percent saturation of hemoglobin. And we call this graph the Oxy-Hemoglobin dissociation curve. And I'll put it up on the screen, that way you guys can see it. Okay, so let's start by talking about the x-axis and the y-axis. The y-axis is the percent saturation of hemoglobin, and this is how much hemoglobin has oxygen on it, right? We just said that. And the x-axis is the partial pressure of oxygen, which can change as blood moves through your body. So the PO2 is different at the lungs than it is at the tissues, because the lungs have more oxygen than the tissues. Okay, so we express PO2 in a measurement known as mmHg, or millimeters of mercury. So the normal PO2 at the alveoli is 100 millimeters of mercury, and the normal PO2 at the resting cell is 40 millimeters of mercury. So look at the top right corner. At the alveoli, hemoglobin is 98% saturated with oxygen. So at the lung, under normal conditions, hemoglobin picks up about the maximum amount of oxygen that it can. It's 98% saturated. But if you keep increasing the PO2 above 100 by giving somebody supplemental oxygen, that won't really change the percent of oxygen hemoglobin is carrying. Hemoglobin will not be 100% saturated until the PO2 is about 650 millimeters of mercury, and we don't encounter those situations in everyday life. So now we see at the top of the curve there's a plateau, and even by increasing the PO2, there's barely any change in the hemoglobin saturation. Okay, now find 60 millimeters of mercury on the graph. Now go up. At 60 millimeters of mercury, you can see that hemoglobin is still about 90% saturated. So this means that the PO2 in the alveoli can fall well below 100 millimeters of mercury without significantly impacting the saturation of hemoglobin. We went from 98% with a PO2 of 100 to 90% with a PO2 of 60. But after 60, the curve becomes steeper. So this means that for every point that the PO2 drops below 60 millimeters of mercury, there is a greater impact on the percent saturation of hemoglobin. And remember we said that the normal partial pressure of oxygen in the resting cell is 40 millimeters of mercury. So find 40 on the bottom of the graph. Now go up. At a PO2 of 40, hemoglobin is 75% saturated. This means that 75% of hemoglobin's binding sites have oxygen on them. And this means that at the cells, hemoglobin releases a quarter of the oxygen that it's carrying. The remaining oxygen stays on the hemoglobin in case metabolism increases. So let's do a little math here. At the normal resting cell, hemoglobin is 75% saturated. And at the alveoli, hemoglobin was 98% saturated. 98% minus 75% is 23%, which means that at the cells, since our percent saturation of hemoglobin went from 98 to 75, that at the cells we have offloaded 23% of the oxygen that our hemoglobin was carrying. So metabolism can actually increase when we exercise. And a PO2 of about 20 millimeters of mercury is about average for an exercising muscle cell. So find 20 on the bottom of the graph. Now go up. At a PO2 of 20, hemoglobin is only 35% saturated with oxygen. And what did we say that a normal cell was? At a normal cell, hemoglobin was 75% saturated with oxygen. So just by dropping our PO2 from 40 millimeters of mercury to 20 millimeters of mercury, that is, just by exercising, we made our hemoglobin release an additional 40% of the oxygen that it can carry. Okay, so one fun fact before I leave you. So let's talk about blood doping. So blood doping occurs when athletes train at higher altitudes. So at a higher altitude, there is a lower PO2, and this lower PO2 tells the body to produce more hemoglobin, that way it can carry more oxygen. And it does this because it needs to carry as much oxygen as it possibly can, that way it can accommodate for the low PO2 level in the atmosphere. So athletes go to this higher altitude and they're training and they're building more hemoglobin, that way they can carry more oxygen. Then they come down to a lower altitude wherever their race or competition is, and they compete in that race. Well, what does this do? It actually gives them an unfair advantage because all that extra hemoglobin carries more oxygen. And if those athletes have a better oxygen reserve, then they can fight off muscle fatigue. Hey guys, welcome back. I hope you understand oxygen transport a little better. This information will come in handy when we start to look at anemias and ABGs. Next lesson, we'll take a look at the things that can change the oxy-hemoglobin curve. If you got value out of this video, then show some love by tapping the like button. Subscribe and hit the bell icon so you're notified every time that I post. Stay safe, and I'll see you guys in the next video.